Good morning, everybody. Today we will continue with electromagnetic waves. We have started on Tuesday, and we will try to finish today with the sinusoidal electromagnetic waves, standing electromagnetic waves, and also energy and power in electromagnetic waves. So today we will try to finish all that topics. Let's try to start with the sinusoidal electromagnetic waves. During the last lecture, we have seen plane electromagnetic waves. You can check your lecture notes. And what we have learned during the last lecture, that in order to produce electromagnetic radiation, we need an accelerated charge, right? If you accelerate a charge, then it emits electromagnetic radiation. So what happens if you have an oscillating point charge here, okay? If we have an oscillating point charge, then we can produce electromagnetic waves in any direction, okay? Here we have an oscillating point charge and it produces electromagnetic waves in any direction. But what about the plane waves, which we have discussed during the last lecture? In plane waves, we have electromagnetic wave in one direction, in certain direction, okay? So just consider that we are far from the oscillating point charge. So just consider that position, okay? This position is very far from the oscillating point charge. And if you choose a very small area here, you can consider that it is also like a plane wave. So, but what is the main difference? In plane waves, electric field and magnetic field are uniform. But in case of sinusoidal electromagnetic waves, we have time-varying electric field and time-varying magnetic field. So this is the x-axis, this is the y-axis, and this is the z-axis. Let's consider that we have electric field component of the light along the y-axis and magnetic field component along the z-axis, and this is the propagation direction, okay? The light propagates with the velocity of light with c in positive x direction. So it is determined by right-hand rule. I have shown that one during the last lecture. So what do you see here? The important thing is here, the electric field is changing by time, okay? So magnitude of the electric field component and also its direction changes by time sinusoidally. What about the magnetic field? In a light, in electromagnetic waves, electric field and magnetic field components are always perpendicular to each other, and they are also perpendicular to the propagation direction. But what you see here in sinusoidal electromagnetic waves, we have magnetic field component, which is also changing by time. The magnitude of the magnetic field and also its direction changes as a function of time. So they are in phase. There is no phase difference in between. So maximum of the electric field and maximum of magnetic field occur at the same time, and minimum of the electric field and minimum of the magnetic field also occur at the same time. But they are changing as a function of time, you see here. So these are called as sinusoidal electromagnetic waves. So here we see an electromagnetic wave, a sinusoidal electromagnetic wave traveling in the positive x direction. Here we have another electromagnetic wave which is traveling in negative x direction. Okay, it is traveling in negative x direction. Again, we have 90 degrees between electric field and magnetic field components of the light, and they are also perpendicular to the propagation direction. So now let's try to describe that electric field and magnetic field as a function of time. We can describe them by using wave functions. We have done it in chapter 15 during the first semester. You can check your lecture notes to remember. So this is the electric field, and electric field changes as a function of time. So electric field depends on both x and time. So what do you see here? This is the electric field. When the x is here, when the x is here, when the x is here, we have different electric field components, okay? And of course, as a function of time, electric field component also changes. So now let's try to write this one. This is the J is the unit vector along the y direction, and then E max electric field magnitude. This is the maximum value of the electric field, maximum value of the electric field, maximum value of the electric field. This is the E max, and times cosine kx minus omega t. So what do you see here? We have k here, wave number, and position. Here we have angular frequency and time. So electric field changes as a function of x and time. So it is changing sinusoidally. So in addition to that, the magnetic field can also be written in that form. Now here we have k unit vector. Since the magnetic field is along the z direction, we determine it with the k unit vector, okay, along the z direction. So here we have B max, maximum magnetic field, maximum magnetic field component, maximum magnetic field component, and cosine kx minus omega t. So the important thing is here that we have two k's here. One is here, another one is here. So please don't mix them. This is wave number, and this is unit vector along the z-axis, okay? So they are completely different things. So this EYXT and BZXT represent instantaneous values of E along the y direction and instantaneous values of B along the z direction. So what do you see here? This is the electric field, let's say when the time is 0, and after certain time electric field is like this, and after certain time electric field is like this. It is also same for the magnetic field. So for this reason, this values gives us instantaneous values of electric field and magnetic field components respectively. And here we have k and omega. By using that k and omega, we can get the speed of light, okay, which is given with that expression. C, speed of light is equal to omega over k. So remember again chapter 15 to calculate the velocity of the wave from the wave function. And this speed of light is also given with that expression, lambda times f. This is the wavelength of the light. This is frequency, which we have seen also this equation on Tuesday during the first lecture of electromagnetic waves. So here we have electric field magnitude. Here we have magnetic field magnitude, and we have such relation in between. So electric field amplitude is equal to C times magnetic field amplitude, speed of light in vacuum. And we have this type of relation between E and B. We have also seen this one during the last lecture. The speed of light can also be written with that expression, which we have also done it during the last lecture, 1 over square root of epsilon 0 mu 0. This is electric constant, this is magnetic constant, but these are for the vacuum, okay? But in case of matter, so electromagnetic waves can also propagate or travel within materials, okay? If the electromagnetic material is traveling in material, then instead of epsilon 0, we should use this one. Instead of mu 0, we should use this one. This is the electric constant, this is magnetic constant, but for the electromagnetic waves in a matter or in a material, we have to use permittivity of the electric material and permeability of the electric material, okay? These values change from one material to another material, and this is the dielectric constant of certain material. We have seen this one in chapter 24, and here we have Km, relative permeability. This also changes for different materials, but it is usually around 1, okay? So for many materials. And we have also seen this one in chapter 28. So electromagnetic waves traveling in vacuum with the speed of light, okay, which is given by that expression. But if they travels in matter, in materials, then we have to use permittivity of the electric material, permeability of the electric material instead of that constants here. Don't forget this one. And for the electromagnetic waves in matter, electric field component can be written V times B. This is the velocity of light in material, and the B can be written with that form, epsilon mu V times electric field. So we have also done this one for the vacuum during the last lecture, and for the material, they are written like this. So then speed of electromagnetic waves in a dielectric material can be written with V, and it is equal to 1 over square root of epsilon times mu, permittivity, permeability. So look at this one and look at this one. Just use this one and this one, epsilon 0 k and mu 0 times km, put them here, then you can get this type of expression, 1 over square root of k times km times 1 over square root of epsilon 0 times mu 0. So what was this one? This is c, velocity of light. So instead of this one, you can use the speed of light. So this speed of electromagnetic waves in a dielectric material or in a matter can be written with the speed of light in vacuum and with that constants. What do you see here? If you take this V and put it there, and if you put this one here, you can find the index of refraction, N, and this gives us the ratio of the speed of light in vacuum to the speed of light in a material. And it is very important number in optics, index of refraction. So it is given with that constant for certain materials. And here Km is around 1. So we can write it like this, square root of K, the electric constant. Do you have any question here related to the electromagnetic waves in matter? Okay. Let me discuss one example. So the electric constant of water is about 1.8 for visible light. So the speed of visible light in a water, what you see here, that is slower than in vacuum by a factor of this one. So instead of K, just use 1.8, then we can find 0.75. So what is the meaning of that? The speed of visible light in a water is slower than in vacuum. Okay, here let me discuss the first example, electric and magnetic fields of a laser beam. Laser is also a sort of electromagnetic wave. So here, what is the question? A carbon dioxide laser emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. Okay, the wavelength is 0.6 micrometer in the infrared region. During the last lecture, we have seen electromagnetic spectrum. Okay, so what was the wavelength? 10.6 micrometer. Wavelength micrometer is this one, 10 to minus 6 meter. Okay, so it is located in the infrared region, carbon dioxide laser. So, and the electric field is parallel to z-axis. Electric field is parallel to z-axis, magnetic field is parallel to y-axis, and this is the propagation direction. Maximum value of the electric field is given by 1.5 megavolt per meter. Write vector equations for electric field and magnetic field as functions of time and position. So let me give you short information about carbon dioxide lasers. Here we have two applications. They are used in medicine for surgical applications, especially in plastic surgery, let's say, and also in industry to cut and weld the metals. So the carbon dioxide lasers are widely used. So what was the question? The question, write the vector equations for E and B as functions of time and position for the carbon dioxide laser. Okay, so we will calculate electric field and magnetic field as a function of x and time. So E max is given within the question, and also wavelength of the light is also given, lambda. And we need k, we need omega, and also we need B max to write down that equations. So we know that E max is given by C times B max. If you take B max from that equation, we can find B max. So E max is given 1.5 megavolt per meter, put it there. And this is the velocity of light in vacuum. Then B max is given by 5 times 10 to minus 3 Tesla. So lambda is given 10.6 micrometer in the infrared region, somewhere here, wavelength of the carbon dioxide lasers. And K can be calculated by using 2 pi over lambda and 2 pi radian here. And then lambda is given, put it there. And then we can calculate K 5.93 times 10 to 5 radian per meter. And we need omega. Omega is given by C times K. Just look at this one. Where is it? This one. Okay, C is given by omega over K. If you take omega, we can write it like this. C times K. C is velocity of light, speed of light in vacuum. And K, we have calculated here, propagation vector. Put it there. And then omega is given 1.78 times 10 to 14 radian per second. In order to write electric field as a function of x and t, just put E max here. This is K, yk, because electric field is parallel to z-axis. Okay, we use here unit vector for the z-axis. And then this is maximum electric field, and cosine, instead of K, just use this one, x plus, instead of omega, just use this one we have calculated here. So just do the same for the magnetic field. We have calculated B max here, put it there, and K times x plus omega times t. So here we have another example, electromagnetic waves in different materials. So now let's have a look at the question. Visiting a jewelry store one evening, you hold a diamond up to the light of a sodium vapor street lamp. So you have diamond on your hand, then you are looking that diamond up to the light of a sodium vapor street lamp. This is the sodium vapor street lamp. It emits yellow color, let's say. So the heated sodium vapor emits yellow light with a frequency of 5.09 times 10 to 14 hertz. So look at the yellow light in the visible region. This is the yellow color, and this is the wavelength, and this is the frequency. Look at the frequency. It is around 10 to 14 hertz, you see, within the visible region. So what is the question? Find the wavelength in vacuum and the wave speed and wavelength in diamond. So what about the wavelength of that yellow color of the heated sodium vapor in vacuum, and what is its wave speed and wavelength in diamond? For diamond, K is given, Km is also given, so we can calculate. We will do that. And the second question, a 90 megahertz radio wave in the FM radio band passes from vacuum into an insulating ferrite. This is used to suppress radio interference, okay? Find the wavelength in vacuum. Frequency is given. Find the wavelength in vacuum and the wave speed and wavelength in ferrite material. K for the ferrite is given. Km is also given. So now let's have a look. The first question, what about the wavelength of that yellow light in vacuum? Wavelength in vacuum can be written like this, C over F frequency. Again, remember that formula, okay? Lambda F, lambda times F gives us the speed of light in vacuum. Then put it there, C, speed of light is given, and frequency, where is the frequency? Frequency is given 5 times 10 to 14 hertz, put it there. So finally we can calculate the wavelength in vacuum. Wavelength of the sodium light in vacuum, 589 nanometer. Wavelength of that light, let's say. What do you see here? The wavelength in meter here, and here we have wavelength in nanometer, you see. So what about the yellow light? 589 nanometer, okay, it is somewhere here between 600 and 550. So what is the speed of light in diamond? Then we can calculate it like this by using that formula. Okay, speed of electromagnetic wave in a matter, speed of electromagnetic wave in vacuum, and we have that constants. We have that relation. By using that formula, you can calculate this one. So put the K here, K is given, put the Km here, it is also given, put the velocity of light here, then the velocity in diamond is given by 1.24 times 10 to 8 meter per second. So the speed of yellow light in vacuum is given with that number, but within the diamond, it is slower, you see. And what about the wavelength of the light in diamond? Here we have calculated wavelength of light in vacuum, but what about the wavelength in diamond? Then we need same expression, okay? But instead of C, just use V diamond, okay? Velocity of light in matter, then frequency, then you can calculate this one. So wavelength of that yellow light in vacuum is given with that expression, but wavelength in diamond, 244 nanometer. So it changes. Second question, 90 megahertz radio wave. And what about the wavelength in vacuum? Put the speed of light, put the frequency, 90 megahertz. Then lambda is 3.3 meter. So radio wave, the wavelength is around 3 meters. Look at radio waves, and this is the wavelength, okay, and it is around meter. We have here 3.3 meters, something like this, okay, it is around here, radio waves, FM, AM radio waves. So, and what about this radio wave in a ferrite? So velocity of radio wave in a ferrite is given by, again, same expression, C over square root of K times Km. These numbers are given, put them here, then you can calculate 3 times 10 to 6 meter per second. So speed of radio wave in a ferrite is much slower than the speed of radio wave in a vacuum. You see 10 to 8, 10 to 6 here. And what about the wavelength of the radio wave in a ferrite material? Just same expression which we have used here, V ferrite over F. V ferrite, we have calculated the speed of light in ferrite, and then this is the frequency. Then we can calculate 3.33 centimeter. So in vacuum, 3.33 meter. Do you have any question here in that examples? So then let me continue with the energy in electromagnetic waves. So we know that electromagnetic waves carry energy. The energy in sunlight is a familiar example, and microwave ovens, lasers for surgery, which I have shown you here, and also laser here, okay, to cut or weld metals. So you transfer energy, you carry energy. So how to write that energy carried by the electromagnetic waves? We can write the energy densities in electric and magnetic fields. In chapter 24, we have learned the energy density in electric fields. And in chapter 30, we have learned energy density in magnetic fields. Okay, we have discussed all these things. But what we have in an electromagnetic wave, we have both electric field and magnetic field, and they are traveling in that direction. Okay, so what about the energy, total energy density of electromagnetic wave? Then I can use both of them. This is for electric field and this is for the magnetic field. So energy is traveled in that forms in the electromagnetic waves. Here we have B, and B is given E over C. We know from the previous lectures and also transparencies. Instead of C, I can use this one, okay? Instead of 1 over C, I can use this one. So take this B, put it there here, and finally, I have that expression for the total energy density of the electromagnetic wave. 1/2 epsilon 0 E square here, and this expression here. So if you solve it, you can find this solution. Epsilon 0 times E square is equal to total energy density of the electromagnetic wave. Okay, so we will use them. This is the total energy density. So what about the energy? Energy is written with total energy density times volume. Okay, so here let's consider you have an electromagnetic wave, okay, and it is passing through that area, okay. So here you have energy of the electromagnetic wave, and you carry this energy to that place, okay. Then this energy traveled by the electromagnetic wave can be written in that form. The U is equal to total energy density, which we have calculated here, times dV, the volume here, okay, between two positions, let's say. And total energy density is given with that expression, put it there, and the volume here is given by area times dx, c times dt. C is velocity, okay, this is dx. So this is the volume here, then put it there, okay. So finally we can get that expression. So what do you see here? This energy here, this energy passes through the area in time dt, okay, passes through that area in time dt. But we need energy flow per unit time per unit area. Energy flow per unit time per unit area. So we will call this one with S, capital S. Energy flow per unit time per unit area. So this is the energy passes through the area A in time dt, du, and this is the S, energy flow per unit time per unit area. So we will divide this energy with area and time. So then this will cancel this one, this will cancel this one. Finally, this S, the energy flow per unit time per unit area, can be found in that form, epsilon 0 c e square. This is in vacuum, don't forget. And we can also write alternative forms of that S like this. Instead of C, just use 1 over square root of epsilon 0 mu 0. Or you can solve this one and write like this. Or you can write in that form. So E times B over mu 0. So if you use that relation, where is it? B is equal to E over C, okay, or E is equal to B times C. If you put it here, you can also write that S in the form of E times B over mu 0 in vacuum, okay. For the S in material, of course, you have to use mu and epsilon here. What about the unit of S? Energy per unit time, energy per unit time per unit area, or power per unit area is given with that units in SI, 1 joule per second per meter square. This is joule, this is second, this is meter square, okay? Or we can write 1 watt per meter square. You can carry the energy by using electromagnetic waves. So what is this S? This S comes from the British physicist John Poynting. He introduced the Poynting vector, okay? So we show it with S. And what we have found here, S is given by E times P over mu 0. If you write this one with in vector form, then we have that one, E times P. This is vector product, okay? So the direction of the S is perpendicular to the E and B, don't forget. It is along the propagation direction. This is the direction of the Poynting vector and determined with that relation, E times B. Do you have any question here with the energy in electromagnetic waves? Okay. What we know of that, in sinusoidal electromagnetic waves, this E changes as a function of time. Okay, remember the electric field. It is written with that form. It is changing by time. And B here, this B also changes as a function of time. So as a result, this Poynting vector, okay, will change as a function of time. Then it is better to write the average value of that Poynting vector. And the average of the Poynting vector gives us the intensity of electromagnetic wave. So here we have Poynting vector. It is changing by time since electric field and magnetic field are changing by time. So instead of Poynting vector, we use the average value of it, and it gives us the intensity of electromagnetic wave. So let me do that. Electric field component of the light is given by that expression along the y direction. Here we use unit vector j, E max cosine kx minus omega t. Instead of b is along the z direction, unit vector k, B max cosine kx minus omega t. This is the Poynting vector. Then what we have here, vector product of j and k. This gives us I, and here we have cosine, here we have cosine. This will give us cosine square kx minus omega t. So during the last lecture, we have seen that this will be positive, okay, for each time. This number will be positive. This is also positive. So for this one, the Poynting vector is along the positive x direction. Okay, we have electric field component in y direction, we have magnetic field component in z direction, and Poynting vector is along the positive x direction. So now just write this one, E times B max, E max, B max over mu 0 cosine square kx minus omega t. This cosine square function can be written 1/2 times 1 plus cosine 2 kx minus omega t. So we will take the average of this one. Look at this one. The average of cosine function or average of sinus function is always 0. Okay, they are oscillating around the 0. So this will give us 0 to calculate the average value of the Poynting vector. Then we will have only contribution from this one. So the average value of the Poynting vector is E max times B max over 2 mu 0. So what is this? This average value of Poynting vector is the intensity of electromagnetic waves. Intensity of electromagnetic wave is given by the magnitude of average Poynting vector with that expression. You can also write that intensity in different forms. Okay, so we know that E max is equal to B max times C. So just use this one and just also use that expression for the speed of light. Then you can get different forms of the intensity of a sinusoidal electromagnetic wave in vacuum. What about the unit? Unit of the intensity is the same as the unit of the Poynting vector, 1 watt per square meter. Do you have any question related to the intensity of electromagnetic waves? Okay, here we have solar panels, and you know that the surface of the solar panels are always looking at the sun, right? Why? Because from sun, electromagnetic waves are coming, okay? So this is the electric field component, magnetic field component of the electromagnetic waves, light coming from the sun, and this is the Poynting vector of the light coming from the sun. So if you make that Poynting vector perpendicular to the surface, so you will get the maximum amount of wave energy here, okay? For this reason, the surface of the solar panels are always looking at the sun. Another application of the energy transfer of the electromagnetic waves or energy in electromagnetic waves is the free electron laser weapon. This is very important and new field of science. Free electron lasers are used to produce X-rays. very bright X-rays, okay? They are used for scientific research. I mean, for many fields of science, for chemistry, for biology, for material science, for physics, free electron lasers are used. But recently, they are also used for FEL weapon. So this is laser weapon. So what is the application? Here we have a laser source, FEL laser, free electron laser, and it can carry very huge energies. So here there is an aircraft, or there is another ship, let's say, or there is a missile. Then with laser, you can explode that aircraft or missile here, okay? By using laser, you can kill it. So, and it happens within seconds, very fast. So you can also do it with conventional missiles. So let's say here there is an enemy, and you use, for example, Tomahawk missile, okay? And you can kill it by using Tomahawk missile. But what about the price of the Tomahawk missile? It is around $1 million to explode the aircraft here or ship. You spend $1 million. But in case of free electron laser weapon, it costs $1, okay, for one shot. It is very cheap. So many armies are working on this to install that free electron lasers on their ships. And United States recently installed one of them in one of their warships. You can check in internet. There are many videos on that. Very hot topic in defense industry. So you can transfer energy by using free electron laser, and then this energy hits the metal here, metal of the missile or metal of the aircraft, and it explodes. So another application, bio application, laser surgery. So what do you see here? This is a doctor, and this is a laser, okay, light. And here, what do you see here? This is brain, okay, human brain here. So lasers are used widely in medicine as ultra precise bloodless scalpels. What is scalpel? This is neşter in Turkish, okay? Bloodless scalpels. So you don't use knife here. They can reach and remove tumors with minimal damage to neighboring healthy tissues. So if you use knife, if you use scalpel, you have to work with your own hands, okay? Then you can make a mistake. But with the lasers, tumors can be removed with minimal damage to the healthy tissues. So this is very important application of lasers in surgery. So now let me continue with the examples. Energy in a non-sinusoidal wave. During the last lecture, we have seen plane electromagnetic waves. Okay, in plane electromagnetic waves, the light is traveling in certain direction, and we have uniform electric field and uniform magnetic field components. Electric field does not change by time, magnetic field does not change by time, and also pointing vector does not change by time in plane electromagnetic waves, which we have seen during the last lecture. These are also called as non-sinusoidal waves. So for the non-sinusoidal wave described in the last lecture, suppose that electric field is given by 100 volt per meter or 100 Newton per coulomb. Find the value of B, the energy density U, and the rate of energy flow per unit area, pointing vector. B is given by E over C. E is given, put it there. This is velocity of light. Then you can calculate magnetic field value 3.33 times 10 to minus 7 Tesla. Energy density is given with that expression we have calculated. Look at this one. This is the energy density, epsilon 0 times E square. Okay. Then epsilon 0 is constant, put it there. and E is given, put it there, take the square of it. Finally, energy density is 8.85 times 10 to minus 8 joule per cubic meter, energy per volume, okay? So what about the magnitude of the Poynting vector? This was the last question. It is given by E times B over mu 0. E is given, B is calculated, put the mu 0, and then you can calculate it. Calculate Poynting vector with that number, 26.5 watt per square meter. And what about the energy in a sinusoidal wave? A radio station, which we have also discussed during the last lecture, on the Earth, here we have a radio station, okay? For example, Çamlıca Tower, okay? There are many radio stations in Çamlıca in Istanbul. A radio station on Earth's surface emits a sinusoidal wave with average total power 50 kilowatt. Power of the radio station is given, assuming that the transmitter, this one, radiates equally in all directions above the ground, okay? You emit electromagnetic waves, radio waves, and find the electric field and magnetic field amplitudes detected by a satellite 100 kilometers from the antenna. So the distance between the radio station and satellite traveling around the Earth is 100 kilometers, and detected values of Emax and Vmax are asked. So how to calculate Emax and Vmax? So Bmax is given by Emax over C. Emax can be calculated by using that expression, intensity. Go back. So intensity or average value of the Poynting vector is given by that expression. Here we have Emax. If we know the intensity or magnitude of average Poynting vector, we can calculate Emax. Okay, we will do that. So this is the Emax. It contains average value of the Poynting vector. What about the average value of the Poynting vector? How to calculate it? It can be calculated by power per area, intensity. Okay, intensity, which we have done in the previous transparencies, is the average value of the Poynting vector, and it can also be calculated by power per area. Power of the radio station here on Earth is given 50 kilowatt. Put 50 kilowatt here. And what about the area? Area of this hemisphere, okay, surface area of the hemisphere can be calculated with this one. What about R? R is this one, this distance, okay, from the radio station to the satellite, and put them here. You can calculate the area of that surface, and power per area gives us the intensity. Intensity is given with that expression. Here we have Emax. Then you know the intensity, put it there. You can calculate Emax, okay, in volt per meter. And if you know the Emax, you can calculate Bmax in Tesla. Do you have any question related to that one? So we have seen energy in non-sinusoidal wave, or energy in plane waves, and energy in a sinusoidal wave. So now let me continue with the electromagnetic pressure. Electromagnetic waves carry momentum, and they can therefore exert radiation pressure on a surface. This radiation pressure is given by average value of the Poynting vector over velocity of light, or intensity over C. This is when the electromagnetic wave is totally absorbed. Let's consider that this is the Poynting vector for the electromagnetic wave or light coming from the sun to the panels of the satellite, for example, okay? So if this light is totally absorbed by the panel, this radiation pressure is given by intensity over C. But if this light is totally reflected, then it is 2 times bigger compared to the radiation pressure when the light or wave is absorbed. Here we have a satellite. This satellite is traveling around the Earth, and these are the solar panels of the satellite, and this is the pointing vector of the light coming from the sun. Okay, so the value of I intensity for direct sunlight in the space before it passes through the Earth's atmosphere is approximately 1.4 kilowatt per meter square. So if these panels are perpendicular to the incoming sunlight, pointing vector of the sunlight, the radiation is completely absorbed by the solar panels, and the average radiation pressure is 4.7 times 10 to minus 6 Newton per square meter. So there is a radiation pressure due to the electromagnetic radiation comes from the light, and each type of electromagnetic wave can produce radiation pressure with that expressions. So this is valid for totally absorbed electromagnetic waves, and this is valid for totally reflected electromagnetic waves. So then let me continue with the standing electromagnetic waves. This is the last subsection of that chapter, and it has also very important applications. The most widespread application is microwave ovens. I will also talk about this. So here we have a perfect conductor, and we have one electromagnetic wave which is traveling along the negative x direction, okay? So when it comes to this perfect conductor, it will be reflected back, okay? You have one light which is coming to the perfect conductor, and it will be reflected by the conductor. So here we have an incident wave, and we have reflected wave. So the superposition of incident and reflected waves form standing wave. During the first semester in Physics 1, in chapter 15, we have discussed standing waves. The mechanism is same, okay? So let me draw something here. So let's consider that we have a rope, and when you produce a pulse on the rope, we have discussed during the chapter 15, okay? So this pulse will move in that direction, okay? But if you fix that end of the rope, then you can produce standing waves. So the mechanism is same also for these electromagnetic waves or standing electromagnetic waves. So what we have here, the electromagnetic wave is not moving anymore, okay? It is reflected back. So every point here in X, along the X, every point, the electric and magnetic field vectors simply oscillate like this. So you can consider that this is a standing wave for the rope, which we have discussed in chapter 15. We have knots here, and we have also anti-knots where the amplitude is maximum. Here amplitude is 0, okay? So today we will discuss this one. Let's consider that here we have a perfect conductor, and it is placed in YZ plane. This is the x-axis, this is the y-axis, this is the z-axis, and this conductor is placed in a YZ plane. And we have a linearly polarized electromagnetic wave which is traveling in the negative x direction and strikes this perfect conductor. So we have discussed in chapter 23 that the parallel component of electric field cannot be present on the surface of the conductors. Okay, so here everywhere on the surface of the xy plane or conductor plane, the electric field will be zero, because what we have here, look at electric field, this purple one, let's say, electric field is parallel to this conductor surface, and electric field cannot be parallel component on the conductor surface. We have discussed here in chapter 23, you can check it. So on the surface and also inner of the conductor, electric field will be zero. Okay, don't forget this. So we have electromagnetic wave. It is moving in negative x direction and it hits to the conductor. So what happens due to the electric field of that electromagnetic wave? This electric field component of the electromagnetic wave induces oscillating currents on the surface of the conductor. So we have charged particles in conductors, right? Negatively charged electrons. So due to the oscillating electric field, we will have movement of the charged particles, then we will have current in the conductor. So this current will produce an additional electric field within the conductor, okay? So then the net electric field, which is the vector sum of this one produced on the conductor and the incident electric field. So they are zero everywhere on the surface and inner of the conductor. Is this part clear? If not, let me know. We have electromagnetic wave and it has electric field component parallel to the conductor. And then due to that electric field, which is oscillating, we have charged particles on the conductor and we produce currents. These currents on the conductor produce additional electric field, okay? So then here we have one electric field due to the incident wave, and we have another electric field produced by the incident wave. So since the electric field on the surface of the conductor is zero, then the superposition of the electric field of the incident wave and also the electric field produced on the conductor will be zero, okay? Because electric field parallel to the perfect conductor must be zero, we know from chapter 23. So now let me continue. So the electric field is zero on the surface of the conductor, and we have two electric field components. One is due to the incident wave, and the other one is produced on the conductor. So it is equal to the negative of the incident one, which is given by minus E max cosine kx omega t. This is the incident one, E max cosine kx plus omega t. So you can also write magnetic field also with that form like electric field. Then by using these two equations, we can get solution for the standing electromagnetic waves. So what do you see here? We have cosine kx plus omega t, cosine kx minus omega t. We know from the trigonometry that cosine A plus B is equal to cosine A times cosine B minus sinus A times sinus B, cosine A minus B, cosine A times cosine B, plus sinus A times sinus B, okay? Just apply this rule for this one, this one, this one, and this one. Finally, we will get electric field, which is given by minus 2 E max sinus kx sinus omega t, and B along the z-axis is equal to minus 2B max cosine kx omega t. What we have here, we have electric field and magnetic field components of the standing electromagnetic wave. Okay, here it is oscillating with that frequency and changes as a function of time and x. So the y component of electric field, this one, changes by time and changes by position, and z component of the magnetic field changes by time and changes by position. So what do you see here? On the surface of the conductor, the electric field is zero, because electric field is parallel to the conductor, and we know that if you have electric field on the conductors and their parallel components are always zero. Okay, so when this electric field becomes zero, here we have sinus kx. If x is zero, then electric field will be zero, right? Because sinus zero is zero. What else? Instead of x, if you put pi, if you put 2 pi, this sinus x again will be zero, right? Sinus 0 is 0, sinus pi is 0, sinus 2 pi is 0, okay? So this values of the kx will give us zero electric field. So what is the meaning of that zero electric field? These are the knots of the standing waves, okay? Here, let's say this is the metal plate here. Here we have one knot, electric field is zero here, and electric field is also zero here, here at that position, pi, and 2 pi electric field is also zero, okay? 3 pi electric field is also zero, and here at that positions electric field is maximum, okay? So what about the magnetic field? For the magnetic field here we have cosine kx, B here on the surface of the conductor is maximum. When the x is 0, kx 0, and then cosine will give us 1, maximum, B max here, okay? So if we have here x pi half 90 degrees, then here we have magnetic field is 0, because cosine function will be 0 here and cosine function will be 0 here. So remember the sinusoidal electromagnetic waves. Let me go back. In sinusoidal waves, electric field and magnetic field are in phase, okay? When the electric field is maximum, B is also maximum. When the electric field is minimum, magnetic field is also minimum, okay? It goes like this. There is no phase difference in between. But in case of standing waves, the situation is completely different. There is a phase difference between the electric field and magnetic field components due to that functions. Electric field component is given by sinus function, magnetic field component is given by cosine function. So electric field is here 0 on the surface of the conductor, right here at that point, due to sinus 0, but magnetic field is maximum here due to the cosine function. Cosine 0 is 1, okay? So now let's continue. Sinus kx is 0 when the kx is 0, or when the kx is pi, or when the kx is 2 pi, okay? So if x takes these values, 0, lambda half, lambda, 3 lambda half, then sinus kx is 0, and then electric field is 0. So we are talking about nodal points of electric field. So electric field here on the surface of the conductor, when the x is zero, electric field is zero, electric field is zero here. But electric field is maximum here, electric field is maximum here. So do you have any question here at that point? So like this, if you have a metal plate here, then electric field is zero here, electric field is zero here, electric field is zero here, and at that positions, electric field is maximum. Now let me continue. What happens if we have standing waves in a cavity? What is the cavity? Here we have a metal plate, and here we have another metal plate, and incident wave is reflected from that conductor, and it is also reflected from that conductor. So then finally we have this type of behavior, standing wave in a cavity, like string, okay, or like strings of the musical instruments, which we have discussed in chapter 15. So then the electric field component is given with that expression. Magnetic field component is given with that expression as a function of x and time. So we have nodal planes of electric field. So here electric field is zero, here zero. These are the nodal positions or planes for the electric field, okay? And if the distance between two metal plates is given by L, if the distance between them is given by L, then x is equal to L, and it is also equal to n lambda half. Why I wrote like this? Because since we have metal here, the electric field should also be zero here, because we have discussed at that position, okay, electric field on the conductor, parallel component of the electric field on the conductor must be zero. We have discussed in chapter 23. So if you put another metal here, another conductor plate here, electric field on the surface of that conductor will also be zero, okay? So when the x is equal to L here, the electric field component will be zero. Then you can use that expression. So L is equal to n times lambda half. So if you take lambda from that expression, lambda is given by 2L over n. N is the integer number 1, 2, 3, 4, it goes. And you can also write frequency. Frequency can be written with C over lambda. Then instead of lambda, just put that equation, and then we have that expression for the frequency. So what we have finally, we have that type of behavior. Here you have a metal plate, first conductor, and here we have second conductor, okay? Electric field at that positions, when the x is zero, electric field is zero. When the x is equal to L, electric field is also a zero, okay? Because here we have nodes, nodal points, nodal planes for the electric field, and these are the antinodes for the electric field. Do you have any question here? Standing waves in a cavity? Then let me show you one example. This is a typical microwave oven, and we have standing waves, electromagnetic waves, with the wavelength of 12.2 centimeter. Okay, so the total distance from that metal plate to that metal plate within the microwave oven is around 24 centimeters, something like this, 2 times lambda, okay? And you put food here within the microwave oven. There is a microwave generator. You produce electromagnetic waves here, and they are reflected from that surface, reflected from that surface. Finally, we have that type of behavior. So we have nodes, no electric field here, no electric field, no electric field, and we have antinodes, we have maximum electric field. So what about the electric field? Electric field means energy. Remember our discussion. Look at the energy. Energy is written with electric field, right? If you have electric field, then you have energy. So you can transfer that energy to the foods within the microwave oven, then you can heat them, okay? For the position of the nodes, the electric field is 0. For this reason, there is no heating. But for the antinodes, electric field is maximum, then we have maximum heating. So what happens if you put food into the microwave oven cavity? If you don't rotate the food, these parts will be cold and these parts of the food will be hot. Okay, so you will see lines on the food. In order to provide homogeneous heating of the food, you have to rotate the food within the microwave oven. Then each part of the food will be heated by the antinodes of the electric field. You can see by eye how these microwave ovens carry energy and transfer energy to the medium, to the particles. Here we have a microwave oven in our laboratory at Gebze Technical University, and we have vacuum chamber, let's say. We have some gas molecules, oxygen molecules, nitrogen molecules, okay? So we have also some particles, and the microwave electromagnetic radiation produced by the microwave oven transferred to the molecules within that vacuum chamber, then you can produce plasma. Okay, let me start this one, then you can see it. So this is the diaphragm pump to produce vacuum within that vacuum chamber. Okay, and then you close the door of the microwave oven, and then you set the rate of the power and you start it. So what do you see here? Look at now, you see there is a plasma, okay? Energy produced by the microwave oven transferred to the molecules within the air, and then you can produce plasma. You can see that indeed these guys produce energy. Any question? Then let me finish with these two examples. Intensity in a standing wave. Calculate the intensity of the standing wave. So this is the electric field of the standing wave. This is the magnetic field of standing wave. So what about the electric field and magnetic field for the sinusoidal waves? Let me go back. Sometimes it is very useful to compare them. So in case of sinusoidal waves, we have this component of the electric field and this component of the electric field. Both of them are given by cosine function. But in case of standing waves, the situation is different. What we have electric field component, which is given by sinus kx times sinus omega t, magnetic field component cosine kx times cosine omega t, okay? This is the difference between sinusoidal electromagnetic wave and standing electromagnetic wave. So the question, what is the intensity? So intensity is given with the average value of the Poynting vector. So then let's calculate the Poynting vector. Poynting vector is given by 1 over mu 0 E times B vector product. Just take this E, put it there. Take this B, put it there. So here we have this one. E max, B max, minus will give us positive, okay? And we have that expression here. This is the pointing vector along the x direction, because E is along the y direction, B is along the z direction. Due to the vector product, S will be along the x direction. So this is the pointing vector, and you can also write it like this, okay? But what about the intensity? Intensity is the average value of that vector, okay? If you take the average of that vector, you will get 0. Intensity is 0. Why? Average of sinus function, average of that sinus function is 0. We have discussed all these things during the previous lectures. So then intensity in a standing wave is 0. So standing waves in a cavity, another example. This is example 32.7. Electromagnetic standing waves are set up in a cavity with two parallel highly conducting walls 1.5 centimeter apart. It is like microwave ovens, okay? But now we have much smaller cavity within the question. The distance between the conducting walls is 1.5 centimeter. So the question, calculate longest wavelength lambda and lowest frequency of these standing waves. Lambda can be calculated with that one, 2L over N. For the longest wavelength, this must be smaller, and smallest value is 1. So for the lowest frequency, we need the longest wavelength. Just calculate the longest wavelength, put it there, you can calculate the lowest frequency. And for a standing wave of this wavelength, where in the cavity does E have maximum magnitude? So E have maximum magnitude and E has 0. E has maximum magnitude, maximum magnitude, maximum magnitude on the antinodes and 0 around the nodes. So then this is asked within the question, where in the cavity does E have maximum magnitude? Where is E 0? Where does B have maximum? Where is B 0? So let's start with the A and try to calculate the longest wavelength. Then take 1, L is given, put it there. Lambda 1 is given by 2L, then 3 centimeter. So the wavelength, longest wavelength is 3 centimeter. And the lowest frequency is also given with that expression, C over 2L. 2L is lambda, okay, here, just that expression. So we have 10 gigahertz. This is the lowest frequency. So what about the B, maximum E position? When N is 1, there is a single half wavelength between walls. Okay, so we have calculated lambda is equal to 2L, right? If you take L, what was L? The distance between two metal plates within the cavity. Here we have metal. Here we have another metal. L is distance in between. Okay, you can consider like this. And this L is given by lambda half. So then electric field is 0 here. Electric field is 0 here on the surface of the metals. And electric field is on the center is maximum. And what about magnetic field? Magnetic field is maximum here and also maximum here, and magnetic field is minimum here, because there is a phase difference between electric field and magnetic fields of the standing waves. So with this one, I also finish standing waves in a cavity. And if you have any question, then I will try to answer them. Do you have any question? With that transparency, I finished that chapter. I also finished the semester for that lecture, Physics 2. So we have seen more or less all topics related to the electricity, magnetism, and light. So we have discussed all details and the relation between them. Any question? Okay, then I will close the session. Take care of yourself. Bye-bye.